My presentation this morning is provocatively titled High School Algebra Intellectual Formation, More Harm Than Good. And as Andrew was saying, you know, when you come out of a great book's curriculum, you tend to want to flag a particular book as being important for whatever question you're looking at. So I am going to be talking about Euclid and Apollonius, which hasn't been mentioned yet. Apollonius wrote this wonderful treatise on conic sections. But probably the central figure in what I'm going to be presenting to you today is Descartes, and in particular his book Geometry. I would allow me to say about make the observation about Descartes that I think you could make about Darwin's Origin of Species. I just don't understand how you would work in the field of biology, especially in those areas that pertain to evolution, and not know Darwin's Origin of Species very well. Because all the things that are really great insights and all the things that remain permanent difficulties, they're all there. They're all there in that original work. Even with all the new information we have and even with the breakthroughs in genetics, all of the basic insights and problems are right there in that book. And likewise, I would say, in the way that we have changed the mathematical curriculum with its emphasis on algebra, when you read Descartes' Geometry, the insights are there and the permanent problems are there as well. It really is a book that opens up a great discussion. And I think for many of us, especially if we've had a kind of conventional math formation, opens up a discussion that we didn't even know was there. I want to make clear from the start what I'm not talking about. There's a lot of debate out there right now on algebra and requirements about algebra, but it's really based on kind of limitations on a lot of students who are going through school. So probably the one that is Andrew Hacker, and I have an article by him there from the Sunday Review, and then on the other side there you see an article which is kind of reviewing Andrew Hacker's argument. People who are saying, look, kids graduate from high school with, you know, high-level algebra and trig and pre-calculus is really necessary. Or the kids who are struggling to get through high school because of this. I am not going to be talking about the challenges that algebra gives for lower performing students or students who are somehow challenged in terms of their math ability. The challenge I'm making is at the other end of the spectrum. My complaint is an impact or an effect that I see on students who do very well in math. They are not challenged, they're not struggling, they are good math students. And so I'm not raising the question, is algebra somehow broadly useful such that we would make students study it or not? But what habits does it form in the mind? What habits are being created in many of our high school students when they do well in algebra? I would like to introduce this by calling it Euclidean geometry and PTSD. There are all the beautiful things that Andrew has said about the logic, the reasoning that is behind Euclid and the formative effect it has on the mind. If you've had something like that from the start, then Euclid goes down pretty easy. But in my high school, for example, for 10th and 11th grade, there would be this honors geometry, and those would be the kids that would get Euclid. The regular math students wouldn't get Euclid at all. And the teacher told me that regularly with these in the honors geometry, they'll be getting just part way into Euclid, and already there are students who will have a crisis. I can't get proofs. I don't get this. Now, I have a lovely picture here of students. This is from Thomas Aquinas College, and I think these are students who are in the 2 or 3 week program over the summer. They introduce these students to Euclid. But I remember in the first semester of college at Thomas Aquinas College, where Euclid, all 13 books, is the requirement for the math for the first year. A girl that I, in fact, was really sweet on would always refer to it as Puclid. For her, Euclid was just this thing that was uphill. And again, this was not a girl who somehow struggled with math. This was a girl who had one of these 3.8, 3.9s, did very well in high school math. What it comes down to is that algebra gives them certain habits of mind about what math is about, how it should proceed, and that it's really a form of symbolic manipulation. So the better you are manipulating symbols, the better you, in which there's a lot of verbal reasoning. That's alien to them, and it's alien to their experience of math. Now, we think of algebra as kind of like the 800-pound gorilla. You can sort of bail out of calculus, but you're going to have algebra, and probably you're going to have 2 years of it. And so it's very difficult for us to imagine what a math curriculum would look like without it. But of course, when you read Euclid, the elements, and also this other work that I'm going to be talking about, Apollonius's conics, this is what it is that students who had math in kind of a pre-college level or a college level, this is what they were reading. They weren't reading books, math texts that were primarily algebraic. It's once Descartes, Viet, Descartes, and people who come after very slowly start introducing it, and for a long time it remains at this very high level. In other words, it doesn't trickle down to to what we would call high school or grade schools. So up through the early part of the 20th century, most young people who are being formed in math are being formed in some form of Euclid, maybe being exposed to some form of Apollonius or Archimedes. Andrew did this in such depth that it will allow me to summarize this very quickly. When you're reading Euclid, one thing that strikes you very forcibly is there isn't a goal of coming to formulas and then plugging things in. What you're doing is taking geometrical forms, types, and unpacking the various distinctive properties of those forms. So for example, the first book of Euclid focuses on triangles. And you're going to prove that the interior angles of a triangle are equal to 2 right angles. And again, note that language, not 180 degrees. 180 degrees is not part of that picture. You're not going to be having missing parts of a triangle and you calculate what the angles are that are missing. You are just trying to get down, hey, this figure has these unique properties, and here's one of them, that the interior angles will be equal to 2 right angles. Or again, what we call the Pythagorean theorem, that the squares on the sides of a right angle triangle will equal, the sum of those squares will equal the square on the hypotenuse. That's this unique property of this figure. When you go over at book 3, which talks about circles, that you have a circle, you have a tangent line, that you cannot fit another line in there. That's this unique property of circles. And imaginatively, maybe you can, really, I can't like stick a line in there somewhere. Well, you try that and you get all these absurd results. So this is not only a property of the circle, but curvilinear figures in general, that they're going to have a vertex point and you're not going to, or a tangent point, you're not going to be able to stick something in between there. But notice the idea here. You're not coming up with formulas and applying. What you're doing is focusing on different kinds of things and making clear what the properties of those things are. And you're doing it through demonstration. Just to say something briefly about Apollonius, because that's a kind of takeoff point for Descartes and his algebraic approach. When you go through a standard geometry text now, they will show you pictures of cones being cut. They will show you that these curves that we call parabolas, they're derived from cutting a cone at different angles. I have a nice picture of that in a bit. But the thing that I want you to see here, you come up in a standard text, you come up with formula for these, and then they are one of many formula that you can have for different curves, asymptotes. In other words, these limits that these curves will constantly approach but never reach. Again, that is, but it's not done in the context of what is this kind of curve versus that kind of curve versus this next kind of curve? What do they share in common? How are they different? What you're doing, again, through demonstrations, is trying to see what are the unique properties of the thing. In other words, what makes it what it is, as opposed to things that are similar to it. By contrast, if you think about just the examples that I've been showing you, when a student comes into these things, they're going to see lots of A, B, C, X, Y, Z as early as possible. To my surprise, sometimes as early as second or third grade. They're putting things in a symbolic representation, and as much as possible, trying to get the student the habit of mind of there are certain things that add together or subtract or multiply or whatnot. Here's what the formula is. How do you plug in, plug out, and so on and get results? So when I will talk about the Pythagorean theorem with high school students, for them, they're just locked in as a squared plus b squared equals c squared. And when you draw the picture, they get this very sort of vacant look because they've seen that picture before, but it's not as if the picture ever mattered. So that there would be a reason for this, you could prove it, is something that's very remote for them. Likewise, 132. Yeah, at some point they may have proved that. Maybe these more advanced students did a kind of Euclidean proof, but you want to get that out of the way as soon as possible, because the project or the task is always being able to apply numbers or numerically or symbolic relationships for those figures. If you look over there on the right-hand side, again, for most of us, yes, there was a kind of a nod in the direction of where the curves came from. You'd get a cone and they'd show it sliced in a parabola ellipse, but you want to get that out as soon as possible. You want to see, again, in the high school formation, the curve. You want to see these curves in terms of how they are fitted on a grid. So chances are, if you've had the standard math formation, you think of parabolas, hyperbolas, and ellipse always in terms of an XY axis. But of course, these are curves that they don't come into existence. They don't come into math, come into the human mind in terms of some kind of symbolic representation. Their origin is in terms of thinking of cones and then slicing those cones in various ways. So the picture of a cone and these kind of slices that give you the sections, parabola, hyperbola, ellipse, that's introduced, but it's not dwelt upon. It's not something that's seen as fundamental, because of course, once you start generating those formula, then you can derive those curves without needing the cones at all. So how did we get here? Okay. How did we get from Euclid and Apollonius to now a completely algebraic approach to geometrical figures? A key text, not the only text I've already mentioned yet, but certainly the one that I think ended up having the biggest impact would be Descartes' Geometry. Descartes is in the world that we all live in now. Descartes will have proofs early on in his geometry. There are things that you would recognize as a kind of a Euclidean proof. But even when he does proofs, he's starting to put in algebraic notation. So we're not just talking about lines, we're representing those lines in some way. And the ultimate project of Descartes' geometry is not, as Euclid or Apollonius, to focus on kinds and to, through demonstration, show you the properties, the distinctive traits of kinds. Rather, is the genesis of Descartes' geometry is solving what's called the three-line or four-line locus problem. And I'll talk about that a little bit later. It's a little involved. So the geometry is trying to find general equations, not just for the hyperbola, parabola, ellipse. You know, maybe those have a position of sort of dignity and venerableness for their age, but Descartes wants to be able to come up with formula for all sorts of different kinds of curves, even when they're not strictly constructible or even picturable. So to take something which appears in Descartes' geometry and is sort of you know, a kind of rite of passage for high school math, the quadratic formula. Very often, in fact, I got this picture out of a textbook. You're introduced to the quadratic formula as a formula. Here it is. We highlight it. We put special coloring around, and it really descends from on high, almost like the golden tablets to Joseph Smith. You know, the origin of the Book of Mormon. There's this descent of the quadratic formula, and no math teacher is going to deny that it's provable. But why would you prove it? Here it is, and you're off to the races. One of the great moments for me, a very memorable moment in my math education at Thomas Aquinas College, was junior year. First semester of junior year, we read Descartes' geometry, and I saw that picture right there. There's a triangle, there's a circle, and as I read this thing, I realized this is the geometrical proof for the quadratic formula. The quadratic formula does not just descend from on high. There's a diagram, there's a proof. This is the thing that Andrew was referring to earlier. The great beauty of geometry, among many things, is that here are things that you can see by the light of your own mind. You're not just taking it on faith. And so often in math education, high school math education, it is one accepted axiomatic statement after another, even where you have things that aren't properly axioms. They're formula that have proofs, they have geometrical proofs. Somehow that's unimportant. So the one place in a high school curriculum where you really could have knowledge, where you really could know something, you're denied it. You're denied it because that's not what it's about. It's about being able to derive formula, get the formula, and apply them. That's what it's about. And that takes place in Descartes. Very often you will hear those curves being talked about with regard to an x and a y. Yes, you'll hear them described as a Cartesian coordinate system. Now, what we have in your math textbook, if you pick up Descartes' geometry, you're not going to see something like these two lines at right angle, what Descartes does. But if you're wondering, where did it come from that we would describe curves in relation to straight lines and quantify those relationships or ratios, that comes from Descartes. Descartes is the one who develops this way of generalizing curvilinear relationships to a pair of straight lines, and that becomes the essential way of describing it. So Descartes is not going to have some whole section on parabolas or a whole section on ellipse, or that's not about. It's identifying essential traits. It's about being able to you would be able to apply it. So to take one aspect of this, when we think of the terms ordinate and abscissa, if you remember back to, if you teach math, you see this all the time, but if it's been a while, that you have your x, which is your ordinate, your y, which is your abscissa. You have these straight lines, and then the curve is generated in relation to those straight lines. Okay, so straight lines first, curve later. That, of course, is the opposite of what it is that happens in Apollonius. It's the opposite of what happens in, if you like, the Euclidean approach to curves, because it's the cone that's first, then the cutting of the cone. Then when you have these curves will have special relationships to straight lines that are within the curve. So generally that line is called the diameter, and the hyperbola is called the hyperbola because there's a relationship on those lines that when you consider those lines as sides of a rectangle, it exceeds by a certain amount. When you look at the ellipse and you look at, again, this relationships that's built on these straight lines, it is deficient. Ellipse it comes from a Greek word which means to lack, just equal. It doesn't exceed, it doesn't fall short, it's equal. Okay, so in other words, curves, then lines, and these lines have distinctive properties. So what happens in Descartes is that this is reversed. You think about those straight lines and then creating curves symbolically through these various relationships those curves have to the straight lines. Okay. Now, some of you may at this point be feeling, so what? Euclid and Apollonius, they talk about geometry one way. We talk about it a different way now. Couldn't this be a matter of preference, or couldn't this be a matter of style or approach? Well, again, remember what I'm focused on here is not whether there aren't a wealth of truths that can come about through the way that Descartes does it. We are talking about how are you forming young minds? How are you forming them through what you're using? When you have the emphasis on curves as coming through these straight line relationships, the whole geometrical origin of the conic section falls out of sight. You have a kind of an obligatory picture in there, but the student is not supposed to think about how it is that the curve actually came into existence in the first place. When you're working with how that curve came into existence in the first place, you are working with the way that the mind naturally understands. Conic sections are cutting the solid figure, which came into existence by swinging a line about that made this conic surface. That's how the imagination first came to know these things. At the point where Descartes is taking off, you already, as it were, have all that down, and now you're moving beyond it. Are our 12, 13, 14-year-olds really safe to just sort of move beyond this thing that they haven't really grasped in the first place? Another important point, I think, is that when you think of these curves in relation to an XY axis, you are thinking of those curves in terms of these external relationships. In other words, I could have these straight lines almost at any old angle and generate certain relationships that those curves will have to the straight lines. But when you look at those properties in Apollonius, in other words, your diameter, your abscissas, your ordinates, they are coming from in the curve. They're coming from the curve itself. So what you're doing is focusing on things that in a way are exterior and perhaps accidental, to the detriment of things that are intrinsic and that are essential. In fact, you don't really even think about it that way. That students, as they are going through math, are not thinking about essential traits, accidental traits. Those kind of things are not there, especially, of course, once you get into that symbolic representation, because a symbol could be expressing something that's essentially true, but it could also be expressing something that's accidental, that again is extrinsic, it's from the outside. Finally, that you look at the conic sections, let's say circle and ellipse, you think of them as equivalent in a way. In fact, you could even, if all you had were the formula, you could consider the circle as a kind of a special case of the ellipse. But of course, that's not true at all. You wouldn't have ellipses unless you had circles first that make cones that can then be cut. Notice there's a sort of natural relationship: circle, conic surface, conic section, right? It's sort of accidental that you could cut the cone in a way which would generate a circle. So again, you're de-emphasizing things that are essential to these, and you're treating things that are in fact genetically related to each other, that is circle to the to the ellipse. You're treating it as if they were sort of all equal, as if they came into being all at the same time. So how does this impact the way that math is taught? For most of our students who are coming through, math is not so much about truths or knowledge as it is about solving problems. To give an anecdote perhaps that I give because I don't think it's unusual. I remember asking my sister, she was very good at math, always got A's, and I asked her, what's your favorite? Well, what is it you like about algebra? It was a little bit of a surprise to me. And she said, because it makes no sense. You just accept, you just sort of creatively feed it from there. When I would ask my teachers in high school, I thought of this immediately when Meryl and Andrew were talking about how do you reach younger students to generate wonder in math and in these things. I remember asking my math teachers, why is it that we have to study these things? And what they told me was, because this is what you need to get into college. If you want to completely crush the soul of a student in terms of opening his mind to wonder, give an answer like that. Give an answer like that. If you're worried that there's some little germ of wonder that might be, generating there, that will stifle it. Okay. So back to our program here. The other problem I see that by this emphasis on abstract formula that homogenize, you really are losing a sense of essential natures. It is not easy to talk about essential natures when you're talking about animals or all sorts of things out there in nature. In fact, when you have the periodic table of elements, it's very difficult for you to think of those things as essential natures, and somehow it makes it different. It's very difficult, in other words, for kids not to look at that periodic table and not think of it as these things are really kind of they're qualitatively different just because you're adding more different kinds of stuff. Okay, here's an area where you actually could be grasping essential differences, and you're tabling it. You're not exploring it at all. The kid very quickly gets the idea. Don't ask those kind of questions. Here's the formula. Apply it. Okay? And then finally, all of that symbolic manipulation de-emphasizes logical relationships. That's why these kids are coming over to Euclid and saying, I call them proof exercises that they have in the geometry book. It's just a punishment, something that they have to get through. And even the little that they do doesn't help them develop their mind anywhere else. In fact, generally, I would say that I teach religion, I teach sophomores, juniors, sometimes I teach seniors. Is in the conventional math program, relationships, reasoning, demonstration, zero. There's nothing for me to use. I will try periodically to put up things from Euclid, but honestly, I find the students are actually too traumatized by Euclid to get anywhere. The moment I start drawing a geometrical diagram on the board, they get a deer in the headlight look. Because the little that they get is so at odds with the whole rest of what it is that they're getting that it's almost worse than the little that they've had is almost worse than not having it at all. Let me end with some observations from the literature on this change in mathematics from the second half of the 19th century. Up to about the 1860s, 1870s, in England, Euclid was the standard text for geometry. And you have to remember that we're not talking about kids that would really be high school age. We're talking about kids, generally boys, that were about 12, 13, 14 years old. Oh, I see a hand. Maybe I should, what's the hand? Raised hand. What, Jeanette, did you want to ask something real quick? I don't even know if I'm supposed to call on people. I might be doing something bad. So Jeanette, put your question in the chat and I'll get back to you. Let's do that. Put your question in the chat and I just have a couple more slides and I will get to you right then. Where was I? Oh yes. So in the 1870s, 1880s, this is where the transition happened, moving away from Euclid to what were considered more accessible forms of geometry. And then ultimately that led to a kind of algebraicizing of geometry. That was something that happened at the turn of the early part of the 20th century. So here's W. Rouse Ball in his short account of the history of mathematics. He has a long section on Euclid, and he concludes the propositions in Euclid are arranged so as to form a chain of geometrical reasoning, proceeding from certain almost obvious assumptions by easy steps to the results of considerable complexity. The demonstrations are rigorous, often elegant, and not too difficult for the beginner. Okay? This is what it is that Andrew was helping us to see with examples in that first talk. And then here's the point I want to make from this. As far as I can judge, boys who have learned their geometry on the new system know more facts, but missed the mental and logical training which was inseparable from a judicious study of Euclid's treatise. Rouse Ball makes in 1888, I would say, is more true now. And please, I'm not talking about the students who struggle in math. I'm talking about the A students in math, that the math that they take and the way that they study it does not allow for a mental and in particular a logical training. It's about symbolic manipulation, not about being able to order concepts, to look at what's assumed, what am I trying to demonstrate, what are the logical links that connects them. James Wilson, 1869, so this is earlier, he was one of these folks who was on the one hand arguing that Euclid was too hard, but he wrote a text that tried to take the essentials of Euclid and make it easier. Maybe Euclid without tears might be a way of putting it. Wilson is one of the people, by the way, attacked by Charles Dodgson. If you're not familiar with Charles Dodgson, you're probably more familiar with his pen name, Lewis Carroll. Lewis Carroll wrote a book defending Euclid. It's called Euclid and His Modern Rivals. And it's a strange book because a lot of it is in the form of a dialogue, almost like a Socratic dialogue, but he defends using Euclid and not ditching it for other things. And Wilson is one of the folks he attacks. But this quote is something that I think Wilson's right about, because even though Wilson thought Euclid was too hard, he didn't want to get rid of Euclidean geometry. Here's what Wilson says. The merit of Euclid's treatment of geometry consists in his resolutely fixing the mind on things with which the argument is concerned and never allowing the substitution of mere symbols. Algebra fails as a discipline precisely because it speedily degenerates into a manipulation of symbols. In Euclid, every step is planted on firm ground. Geometry, treated algebraically, would lose this merit altogether. I have further reading here. There's a wonderful book on Apollonius. First you want to read Apollonius, but in terms of making some of the points of how it's done differently now versus in the past, Michael Fried and Sabate Unguro. Usually if you read articles, you read things out there that criticize the way in which algebra impacts the mind. As you keep reading and you look at references, you are going to run into Jacob Klein's Greek Mathematics and Greek Mathematical Thought. Actually, I have that's a typo, but Greek Mathematical Thought and the Origin of Algebra. You are going to see that referred to, because Klein was one of the people in the early part of the 20th century who was the most articulate about this. And then finally, David Lachterman. David Lachterman has a very difficult book called The Ethics of Geometry, in which he criticizes, or at least contrasts in an argumentative way, Apollonius versus Descartes. But a more accessible thing is this short article that he did on these essays on Descartes' meditations, where he points to these key differences between Descartes' approach and someone like Apollonius, somebody working in the Euclidean model. There's much more to say about this, but I've tried to hit what I consider the thing that students shouldn't have Euclid, or sorry, shouldn't have algebra. I'm not saying that algebra is bad. Descartes shows you the power of algebra. It's one of the great things about that book. The issue I'm raising here is, should we be forming minds with it? Should we be forming minds with algebra instead of Euclid? And I would submit that what I see, especially working with students where I'm doing apologetics, where I'm doing reasoning about the faith, I should be working with students whose math is helping them to reason. And I find as a teacher exactly the opposite, that what they're learning in math is harming their ability to reason. So I'll stop. Questions, objections, I'll let Andrew moderate. I'll get rid of this. Stop sharing. Okay. Geometrical. Let's see. Yet geometrical figures are involved in real estate purchases, architecture. Bill, I'm not disagreeing with you, but as in my neck of the woods, I need students to understand given, to prove, logical links. You're right that geometry can be applied, but oh, I have to read your earlier. Thank you, Bill. Okay, reading. Agree with Arthur. How many times have you used quadratic formula, logarithms, absolute values since leaving high school? Yeah, but I guess I don't know that I've used that geometrical stuff either. And probably to the point that I have used it, I've screwed it up. I don't. But certainly what I've used are the truths. Certainly what I've used are the habit of mind. Where am I starting? What's the principle? What is the kind of the logical link or essential connecting link? But let me affirm what you've started there. Bill, I will tell people, if we're defending algebra on the grounds that it's practical, I don't know that's going to cut it. I haven't solved for X in 30 years. That's a lie. It's just a lie that somehow most functioning adults need algebra. Everybody know the way that you know that is completely false is once you have children and they bring their math homework to you. That's how you know. That's when you know. When they come to you in 5th grade and 6th grade and they're getting help for their math and you can still help them, you realize, aha, this is something I'm still using. This is part of the real world. Once you get to like about 8th or 9th grade, no, that is stuff that most, and I've said this to our math teachers. Why do you have a curriculum which really serves about 20% of higher level math? Only 20% of the students. So why are the rest of us getting dragged along for the ride? But even in middle school, once upon a time when these English schoolboys were studying math, age 12, age 13, they were reading Euclid. So you can do it that young. It's not that, you have to be patient. But you recognize, and it isn't just a matter of cramming it. you want them to have some sense of what's going on. So yeah, I think it can be done as early as middle school.
Could we, Mel, are you on here still? Is Michelle still here? I'm sure she has some thoughts. Oh. Okay. Go on to the next one.
Sure. I've got, do I have suggestions for teaching algebra? But certainly you can teach algebra in a way that you ask yourself, what is the geometrical foundation? What is the diagrammatic or geometrical?
These things, the more you actually take the time, maybe with some colleagues, maybe using those Baltina videos to actually work through book 1 of Euclid, the more you do those things and learn it yourself, the more you're going to figure out creative ways to work with your students. And I don't think that a book is going to be able to replace that experience for you. I don't think we come up with a book and give it to you. It's going to really make you better able to be really creative with your students in the classroom, compared to what will happen if you are studying it yourselves for a while, doing some summer time work, and you want the faculty, you want to school to do this if you can, but that's where it's really going to come from. All right, Go ahead, Arthur.
I'm looking at my experience is that students and parents have a severe resistance to non-conventional. I'm not, Kyle, I'm not sure I'm understanding your question. When you say severe resistance to non-conventional algebraic approaches, what does that mean? I always think of algebra as totally conventional. That's what our students do all, year after year after year. Could you want to just explain your question a little bit?
Yeah, I'm sorry. I meant that they're attracted to the algebraic approaches. I didn't mean for that confusion. So you can read that as non-conventional, as a geometric Euclidean type approach. That they're looking for the algebraic and frustrated when they don't find it.
Yeah, because they're worried about getting into college and doing well in the SATs and the ACTs, and they're worried about all that. Again, I think there are ways in which you continue to teach them algebra. I'm not suggesting that you ban algebra. What I'm saying is that this just dominates everything, and there's no time spent on what would allow for argumentation, visualization, all of these other things. And how do you sell parents on that? As long as you can continue to get good test scores, that usually calms a parent's fears. As long as your kids continue to do well on PSATs and SATs and all that, they look at results. On the other hand, I think the thing you also have to make the case for is, over here in, let's say, literature, or over here in, religion or history, your child making this argumentation, there are things that are given, that are assumed. There's something that I'm arguing as a conclusion. There have to be things which are logically related to each other, which are causally related to each other, which got me to that conclusion. That's in math. And that's not what our students feel. Our students feel the opposite. At the point where you think a proof for the existence of God is, pretty easy. I got that. But you look at a proof which is, vertical angles are equal, all vertical or opposite, vertical angles. Like, oh, I don't know about that. Then you really didn't understand the argument for the existence of God. It's just that the conclusion sounded pretty good to you, and all that stuff in the middle was okay. But you never really got that there was a proof there. If you can't prove things about triangles, you cannot prove things about supernatural beings. That's imaginary.
A couple of things I think I wanted to add. One is that it would probably be very good for us to distinguish between what should be required in mathematics, where you're aiming at generally giving a liberal education, and what should be considered a specialist courses for those students and parents who want their students to be able to do college level, to be able to do the college level math and science courses or take them on. That would be a healthy thing to distinguish. And then a second thing is I really would someone go back and invite people to look at the Paul Lockhart books. Paul Lockhart, who's a contemporary mathematician and also a high school teacher in New York City, wrote an article, an essay a while ago called A Mathematician's Lament, in which he, as a mathematician, complained about the lack of what he considers true math education in K-12. He says, what I love to do as a mathematician, that's not taught anywhere to students. And then he wrote a book, or two books, I guess, showing his approach to mathematics in the classroom, which is very different from Euclid's. His is very much more of a discovery process directed effort, though with realizing also the importance of not just the discovery, but the argument and the presentation of your results. And I gave you a link to a video that introduces him and his work with it. So,
Andrew, can I take up some of the comments?
yeah, go ahead.
I just want to quote solving for X. You must not bake much. And the math I'm using is second grade, third grade math. I'm just multiplying and dividing. Yes, I'm totally in favor of doing simple arithmetic functions, but there is nothing from that algebra, ninth grade algebra book that I'm using when I bake. There is nothing from that ninth grade algebra book that I'm using, in the kitchen. No, that's just adding, subtracting, multiplying, and dividing. Jan Herkold, I hope I'm pronouncing that right. To be fair, if you're using spreadsheets for work or personal finance, you're using formulas. Well, I'm not using them. They're in the computer. I don't have to understand what it does. I just plug things in and it does it. And I don't know that there's any advantage in understanding. But remember, my math is defended on the grounds that it's somehow useful. It is useful. I don't deny that it's useful, because engineers and chemists and all sorts of professional people use higher. No, we are not using that stuff. We're not. I'm not using this into it. I good for the mind. Are we defending higher level math because we somehow need it? Are we defending higher level math because it's a career? There are these careers out there, and you got to have. If you ask me, this is a Sputnik hangover. This is a Sputnik hangover. This is this fear that if we don't have lots of math and lots of science, if we don't have lots of math and lots of science, then we'll be cavemen. You know that.
Arthur, Jan wants to say something, so you might. Sorry, I don't know.
Good.
You're up. No, you're not. There you go. Let's say something. There you
Can you hear
go.
me?
Yeah, we got you now, Jan.
Okay, thanks. Yeah, it's Jan Hirschfeld. You're right. Most of the time you use a spreadsheet, you're using the formulas that are already in, but very often you're not. You're trying to figure out something else, and I mean you are using, I think.
I never do this. I never do this. I mean, maybe you do this. I don't.
Well, I used to work in investment banking, and
Oh my
use
God!
spreadsheets a lot.
You are proving my point. You are proving my point.
Well, yeah.
For those of us not working in investment banking.
Yeah, but you're not using higher level math. It's if you're using spreadsheets a lot, unless you're a quant, you're not using what I would think of as higher level math. But I think algebra.
Students, all of our students, to be able to see an algebraic formula, know how to have that kind of skill. But then finance, banking, that they can learn what they need on the job. We don't want to make it so we try to cover all of that stuff in high school and force all students to do that. I think that's. I'm broadly sympathetic to this whole discussion. I just think and I as well. I mean, don't often see the need of knowing about logarithms and sort of things in algebra 2 and beyond. And I wish there were Euclidean geometry in schools, but in very many sort of majors, I believe that too. If they could keep duplicating themselves, California, Massachusetts, one in every state. How about 50? How about 50 campuses? We're working on
one, and being able to solve equations and also create your own equations based on information is useful. That's all I want.
Yeah, and I'm not denying that it's useful, but not for most folks.
I think it's probably the case that for most people who end up going that way, unless they've had a math science track all the time through their education, what they find is they have to relearn a lot, right? You have to, if you realize, I have to actually use algebra, and even I do this with spreadsheets. If I have to use algebra, I have to go back and relearn it. So it's not that I'm remembering everything I did in algebra in high school. I've forgotten most of it. It's just that kind of familiarity with algebraic techniques that's really important. You're going to have to relearn it anyway in specialized tasks.
Can I want to address one thing from the comments here. Zachary Chandler. I think algebra is the wrong target. What you're arguing against is algebra unmoored from geometry, intuition, logical reasoning. It doesn't have to be taught that way. You're right, but that's the neighborhood that most of us are in. So when you say it doesn't have to be that way, you're right, but that's what it is. Even at schools that are trying to have more of a liberal arts emphasis and so on. In fact, let me put it this way: at the beginning of when I was first a college professor, I taught at Xavier University. I'm at registration, and there's a lady there who's from the math department, and I start talking to her, and I say, well, at my school, at my college, we would read Euclid and Archimedes and Apollonius. We read all these, mathematical things, and she says, yeah, but we we've moved beyond that. Modern math is way beyond those things. We know much more now. And I said, well, that's interesting. I mean, because that's something we argue, because we read Lobachevsky and we read Euclid and which one is right. And she just said, well, no, there isn't an argument. I mean, modern math knows more than any of those people know. And I said, well, yeah, that's a possible position. And so what we do is we argue between the moderns. And she said, I don't want to talk about this. I don't want to talk about this anymore. I would say that very often there's just this wall that goes down once you start talking about Euclid and Archimedes and Apollonius as being a kind of a ground or a foundation for these things that come later in algebra. So algebra is the wrong target. You're right. Like in itself, when you look at Descartes, yes, algebra is grounded on geometry. But we live in this post-Cartesian world in which there isn't just algebra as a body of knowledge or a body. There's beliefs. There are dogmas about this. And so it isn't just neutral or value neutral, to use the social science term. I think there are a lot of people who are quite frankly committed to algebra, emancipated from geometry. They're committed to it.
Yeah, no, thanks for that. I agree. I mean, I definitely see what you are saying, and you're objecting to the way in which algebra is being taught and the amount of emphasis and the amount of time that it takes up in the curriculum being taught that way, whether it's algebra or all higher mathematics, which is a problem. I think one of the things that I've found most fascinating as I've gotten more and more into understanding the history of mathematics and thinking about how to do mathematics well within a liberal arts curriculum is that, so Andrew Seeley has brought up Paul Lockhart multiple times, but there are plenty of other names that I've come across and that I could throw out there, whether you want to talk about folks like George Polya and the writing that they did on mathematical problem solving. But really what you just see is you see all these mathematicians that are out there kind of lamenting the same things that we are, or similar things in a way.
Yep.
And yet they're coming at it from just the perspective of mathematicians. They also see that it's a problem that their discipline has become, hijacked by the standardized test makers and the college entrance machine and whatever else. And, math, whether it's geometry, algebra, I mean, in some ways these distinctions are important, but they're also, those two different things are very intimately connected to one another, as I think you pointed out. And yeah, it all has to be grounded on logical reasoning. And I don't think the emphasis, I guess one other thing I push back on is I don't think the emphasis that putting some emphasis on problem solving is necessarily bad either. In fact, I
don't think it is.
Yeah, it's a really hard thing to teach that actually we don't teach very well. The kind of standard programs, probably what you're calling problem solving, I would say is not actually really problems. The students aren't given the freedom to approach a problem with their intelligence and, a set of tools that are well grounded. They're just, here's a problem, here's a formula, and that's not real.
Yep, I agree.
Well,
so
Andrew, I'm sensitive to time.
Yeah,
Andrew, we're probably.
It seems like from your last comment, Zachary, that's exactly the kind of thing that I want people as math teachers to be thinking about. Whatever I'm teaching, am I teaching it with an attention to the beauty and the wonderful insights that this is going to give me? Am I communicating that to my students? That they're not just being made to march through a series of assignments because they need to get into college, but it's because these techniques will help them to see the beauty and the wonder in some aspect of the world.